This video is going to focus on operations with radicals, and as you can see over here we have four main categories that we're going to hit on today. First is adding and subtracting, then multiplying and dividing, rationalizing the denominator, and then lastly the conjugate. Each of these has special rules, and as long as you follow them, with addition, subtraction, multiplication, and division, as long as you follow them, well, it's pretty much the same thing as working with just plain integers. When we get to rationalizing the denominator, that's going to be something that might be new to us, as well as conjugates. Although I did do a video on conjugates with the complex number system, so you could see how it works there and transfer it over to radicals, because it's basically the same thing. But let's get started with adding and subtracting radicals. When we are adding or subtracting radical operations, they must have the same radical. What do I mean by that? If I have the square root of 2 plus the square root of 3, there's not much I can do to that, because what is under the radical, the number under the radical, is different. I can't simplify this down into anything other than a decimal. But if both the numbers under the radical are the same, I can simplify it a little bit nicer. So if this was the square root of 2 plus the square root of 2, well, my answer would be 2 times the square root of 2. Think of it like this. If this is x and this is x, when I add them together, I get 2x. It works the same way with our radicals. As long as these are the same, you can add or subtract them. So, since I just mentioned subtraction, if I have let's say we have 4 times the square root of 5 minus 2 times the square root of 5, they have the same radical. So I know in my answer I'm going to have square root of 5. And now I just have to subtract what's in front, 4 minus 2. And 4 minus 2 is 2. So that would be our answer, 2 times the square root of 5. So we started off pretty simple. Adding and subtracting, the radicals must have the same value. Okay, but let's look at one little more complicated problem, as you will see stuff like this on your homework for certain. Let me erase this here. And let's say we have, I don't know. Let's say we have 8 times the square root of 5 minus the square root of 45 minus, let's go with the square root of 50. Actually, no, not 50. Let's go with 80. Alright, you might be thinking to yourselves, you can't do this. We're going to be breaking our rule because this is a radical with a square root of 5, this has 45 underneath, and this has 80 underneath. This is where it pays to remember how to simplify your radicals though, because even though that these two are different, I can simplify these down to get the square root of 5. Okay, remember we can break this down into a perfect square and a non-perfect square. So this is the square root of 9 times the square root of 5. And this is the square root of 16 times the square root of 5. So now I have those square roots of 5. That means my problem is going to become 8 square root 5 minus, square root of 9 is 3 times the square root of 5. I have to leave square root of 5 as it is because it's not a perfect square. Square root of 16 is 4, so minus 4 times the square root of 5. And now everything has that square root of 5. 8 minus 3 is 5. 5 minus 4 is 1. So our answer ends up being 1 times the square root of 5, or just square root of 5. So there you have it, adding and subtracting radicals. Make sure the radical portion is the same. Alright, let's move on to multiplying and dividing. Alright, with multiplying radicals, we do not have to have the same number under the radical, but what we have to make sure we do, and this is my second rule, is simplify the radicals in the end. Do not leave it as an unsimplified radical. So let's look at that original problem that I did, which was the square root of 2, but instead of adding the square root of 3, we're going to multiply by the square root of 3. Multiplying radicals is much simpler in this case. I don't have to worry about these numbers being the same. I can just multiply them together. So what's the square root of 2 times the square root of 3? Well, think of it this way. What's 2 times 3? 2 times 3 is 6, so the square root of 2 times the square root of 3 equals the square root of 6. And then we have to check and see, are there any perfect squares we can pull out? There aren't, so we're done. And that's multiplying radicals. That's basically it in a nutshell. Not too terrible. Let's say I have, let's say I have the square root of 9 times the square root of, I don't know, let's go with 25. Alright, just like before, 9 times 25, that's 225. It's going to be the square root of 225, but we can't leave it like this. We have to see what can we simplify that down to. And it just so happens that, well, the square root of 225 ends up being the square root of 15. Or ends up being 225 is square rooted, becomes 15. So the answer is just 15. How can we get that a different way? Well, look at the numbers that I multiplied by. You could do the simplifying first. 9, or the square root of 9, is a perfect square, so this becomes 3. Square root of 25 is also a perfect square, and it becomes 5. What's 3 times 5? It's 15, so it works out. Now, something you should be careful of when multiplying. It seems simple, but if you're not careful, it can cause mistakes. Let's say we have this. We have the quantity 3 plus the square root of 7 times the quantity 4 minus the square root of 2. What am I going to do here? You might think, oh, I'll just add and then multiply. You're going to deal with decimals. That's not too nice. What this really means is we get to do some distribution. We got to multiply our first numbers first. So 3 times 4 is 12. Then we multiply our outer numbers. So I have 3 times the square root of 2, negative square root of 2, so minus 3 root 2. Then we have the inner numbers, 4 and the square root of 7, both positive, so plus 4 times the square root of 7. And then lastly, multiply the outer numbers. So we've got square root of 7 times the negative square root of 2. 7 times negative 2 is 14. 7 times 2 is 14, and it's going to be negative, so minus the square root of 14. And this looks like we should be able to do stuff with it, but sadly we can't. There's no way we can simplify this down, and unless we take it to a decimal answer, this is what we're going to be left with. So if you see something that looks like you can distribute, you probably should. And then that's going to give us our answer there. Alright, we've talked about multiplication. Now let's get into the sticky subject of division. Alright, now we have dividing radicals, and our rule for dividing radicals is you cannot have any radicals in the denominator. Doesn't matter how it's there, we need to get rid of it. So a lot of the times you'll see division of radicals, or just division in general, shown as a fraction. So like if I have just 3 over 4, the fraction 3/4, this actually means 3 divided by 4. So when we're dealing with radicals, we cannot have a radical down in the bottom. That does not work out. We have to get rid of it. And there's 2 techniques that we're going to be using to take care of those radicals in the denominator. One is called rationalizing the denominator. And the other is called the conjugate. These two methods are how we get rid of our radicals in the denominator. We cannot use both at once. We have to choose one or the other. Thankfully, it's pretty simple on deciding how we're going to choose which one. So let's get rid of the top stuff. Let me erase this up here. And we'll move our text up a little. That way we have some room to work. Let's say I have 5 over the square root of 3. I have a radical in the denominator. Can't keep that. Which one of these do I want to use? If the only thing in the denominator is a radical, you're going to rationalize it. How do I do that? Easy. I multiply the top and the bottom of our fraction by the denominator. So I have the square root of 3 on the bottom, so I'm multiplying top and bottom by the square root of 3. That's going to cancel out our radicals. And this method really is easiest if it's a square root. If it's a cubed root or a fourth root, it gets a little trickier, but we're not going to be talking about those right now. So if it's a square root, all we do, multiply top and bottom by that square root. And what do we get? We have 5 times the square root of 3 on top. And then what happens down here? You have the square root of 3 times the square root of 3. 3 times 3 is 9. So let me write this under here. So I have the square root of 9 when I multiply these two together. But what is the square root of 9? It's 3. So our answer becomes 5 times the square root of 3 over 3. And this is rationalizing the denominator. If we only have a radical in the bottom, we can rationalize it. If there's more stuff, that's where the conjugate comes in. So let's erase this and try a different example that shows how the conjugate works and when we're going to use that. Okay, let's say we have 7 over 3 plus the square root of 2. I have a radical in the denominator, but using the rationalizing method isn't going to help, because if I multiply top and bottom by the square root of 2, it's going to get rid of this radical, but it's going to also put one onto here. So that's where the conjugate comes in. What is the conjugate? The conjugate is the denominator with the sign flipped. So take a look at our denominator here. I have 3 plus the square root of 2. So this time, I still have to multiply top and bottom by something, but since there's an operation here, since there's more than just the square root of 2, we use the conjugate. And the conjugate for this one is going to be, well, 3 minus the square root of 2. All I did was take the denominator and I changed the sign. Alright, so then I've got 3 minus the square root of 2 on top there. And since I have two terms, I have to do some distribution. So conjugate is a little more involved than rationalizing the denominator, but it's not too terrible. So let's work on the numerator first. We're going to distribute the 7 to both pieces. So what does the numerator become? It becomes 7 times 3, which is 21, minus 7 times the square root of 2, which is 7 root 2. There's our new numerator. The denominator, as you're probably noticing, is going to be a foiling distribution, because I've got 2 terms over here and I've got 2 terms over there. So this one is a little more complicated, but it works out really nice in the end. So let's start by multiplying our first terms, which is 3 times 3, 9. Then our second terms, our outer terms, which is 3 times the negative square root of 2. So we've got minus 3 root 2. Then our inner terms, which is the square root of 2 times positive 3, so plus 3 root 2. And then lastly, multiply our last terms, which is the square root of 2 times the negative square root of 2, which gives us the negative square root of 4. Alright, doesn't look too simple right now, but look a little closer. You have the negative 3 times the square root of 2 plus a positive 3 times the square root of 2. These terms cancel each other out. And what is the square root of 4? Square root of 4 is 2. So really, this simplifies down to being 9 from right here minus, alright, so we said the square root of 4 was 2, so it's really 9 minus 2, which is 7. So that becomes our denominator here. 21 minus 7 root 2 all over 7. And usually this is where we can stop. But what do I have here? I've got a 21, I have a 7, and I have a 7. These three numbers all have a common factor of 7. So what can I do about that? Let's move this over a little. Since they all have a common factor of 7, I can rewrite it. I can have 21 over 7 minus 7 root 2 over 7. All I did here was split this big fraction up into two smaller pieces. I can do that because they're all over 7, and there's only one operation here. So I can now simplify this. What's 21 divided by 7? Well, that's 3. And if I look over here, I have 7 divided by 7. What's 7 divided by 7? It's 1. So it's 3. These basically just cancel each other out. And we're left with 3 minus the square root of 2. And that is our final answer. So this one turned out to be a lot more complicated than originally thought, but it really wasn't too bad. We had to use the conjugate so that we didn't have a radical in the denominator. Remember, the conjugate is just the same numbers in the denominator, but we changed the sign. Multiplied top and bottom by the conjugate, had to do some distribution. Key thing here, when you do the conjugate, your denominator will become a single integer. If you get more than one number in the denominator, I'm sad to say you've done it wrong. So, if you do the conjugate method correctly, you're going to have a single integer in the denominator. Then, check and see, can you do any distribution? Or sorry, not distribution, simplification. Always, always, always simplify. And that, ladies and gentlemen, is operations with radical expressions in a nutshell. I know this video was a little bit on the long side. Hopefully, it wasn't too tough though. And good luck with your operations with radical expressions.